Hi, good morning, almost good noon. Welcome to this talk. Thanks for attending this talk about quantum computing in Java, an exceptionential opportunity. I had to practice a long time to speak that word exceptionential. I typically am very careful when choosing what I'm saying, but this time I didn't think about it too much. So it's actually a combination of quantum computing is something exceptional. And one of the things that speed up quantum computing is because it's exponential. Okay, I know that the DevOps audience typically doesn't laugh with physics jokes, so I'm not even going to try that. By the way, I'm not going to talk about UFOs here. So, about me, quite a few things. I'm mainly working with Java, but I have a background in engineering and physics. So I'm hopeless between two chairs, between the scientific chair and the IT chair. And I see that there's a huge gap between those two worlds, and that's something that I hope can be fixed one day. So if I actually prepared this presentation, so I did a Google search on quantum computing. ChatGPT is too advanced for me. And when you search for quantum computing, you see quite a lot of news items, and that's a good sign. It shows that quantum computing is popular. It also makes it harder to detect the high-quality articles from the pseudoscience and and the clickbait. Also sorry for the slides. I didn't use AI to generate them. This is just what PowerPoint said. So I typed in, why am I looking into this? And then PowerPoint suggested this picture. So I said, yeah, why not? It's probably cool. So why am I looking into this? Why am I'm typically spending most of my time with JavaFX. I'm the co-lead of OpenJFX, making Java on the client work. Not that that is such a lucrative business, but why am I spending then so much time also on quantum computing? I think if you look at what we can expect from quantum computing, there are many things that are extremely important, and I'm not going over this list now. But I think everybody's talking about the world is changing, and it's not like it used to be, and we live in strange times, and so, and yeah, that's true. There are many challenges, and I'm personally convinced that quantum computing can help us with many challenges. It's not that I want to say let's just hope that technology will solve everything, and we as humans we don't need to do anything. Totally not. But I think that quantum computing is really, I'm hoping that it can make life on Earth better for everyone. And that sounds maybe high level, but it really comes, it's really very concrete because quantum computing can help with drug discovery. And I think that would be a major win. The typical applications that you know is it can break encryption, or it can make encryption more secure, which is what I personally like more. But there are many things where quantum computing can have an impact. And then one of the probably the number one question that I get when I talk about quantum computing and Java is, why are you doing this in Java? Because Java is a language for cloud development, and by the way, Java is dead. And so lots of questions about why are you doing this in Java? I think there are many reasons why one wants to do this in Java. There's a huge developer base, so all those people who know Java, and there are quite a lot of them, they can also become they can also leverage quantum computing. So I don't really like the idea about let's now educate a total new class of developers, quantum developers. We already have so much experienced developers, so if those can use quantum computing, that would be great. And Java is a great language for scientific applications, for lots of other applications. And there's lots of progress recently in the JDK, in OpenJDK, that is really important to scientific work, like the Vector API, Panama, and all the low-level things that make Java more relevant in the computational areas. And then actually, especially, one of the key reasons why Java exists is it is a blue-collar language. It is a language that's being created to get the job done, not to win a prize for the most hip language, but it does help you achieve what you need to achieve in a maintainable way. And I think that's really important for quantum computing as well. So, outline, I'll briefly talk about high-level quantum computing API in Java, which is how you can use a quantum computing API today in Java. Then I will dive a bit into why is quantum computing special. And this is the part where I think you need to make sure that people can leave the room. I hope nobody is leaving. And actually, I wanted to ask people if they are leaving, why are you leaving? Am I going too fast, too slow? So I wish there was an indicator for that. But it's very hard to do this talk, actually, because for some people, this will be amazingly slow because they already know the things. And for other people, it might be way too fast because I'm skipping a few things. My fellows from the DevOps steering committee on the second row, if they dare to leave, it's just because it's way too fast for them. So, and then I will talk about why is it performant, and I will make sure to reserve 10 minutes time for the quantum simulator. So I will probably not show all the slides in why is quantum computing special. So I did a poll on Twitter, formerly called Twitter, to try to understand what are people mainly interested in. And because those three areas, are you interested in quantum physics? Or do you want to use this in Java, to use it in one of your current or future projects? Or do you want to create quantum algorithms in Java? Those are different areas which need more than one talk by itself. And you see that the majority was, I want to use this in Java, which is what I kind of expected and hoped for. But of course, this requires talking about the other things as well. So let's, oh yeah, by the way, I have some giveaways, book and T-shirts, and I'm not sure how to give those away because I really my goal is that people here and everywhere can use quantum computing to do great things. So if that can help, well, the T-shirt, I'm not sure how that can help writing great code, but anyway. That would be, that is actually my preferred way of helping people. So let's give an example, the most popular example, but the one that I'm personally not very excited about, but because it's popular, it needs less introduction. Quantum computers are expected or have the possibility to break encryption in the future. It's not even certain that this will ever happen. It may happen or it may not happen. And that's why you hear lots of talks about post-quantum cryptography, because people want to prepare themselves for this. It's a pretty defensive way. I would rather recommend do quantum cryptography, which is more constructive. But let's just talk about the encryption here. So many encryption techniques are based on the fact that it's easy to do one thing, but hard to do the reverse thing. So if I was good with PowerPoint, I would have made this a quiz. Then I would have shown 119 equals, and then someone who guessed it's 17 times 7 would win a T-shirt or so. But as you can see here, 17 times 7 is 119. That's easy. That's something that you can calculate out of your head. Actually, I didn't. I did it out of my head. I didn't use a calculator, so I hope it's correct. But the other way around, if I tell you 119, how can you decompose that in the product of two prime numbers? Then that's harder. I mean, for 119 it's still easy, but for large numbers it's pretty hard. Well, it's actually very hard on a classical computer. And that's why it's why using this in encryption is so secure, because A classical computer, if it wants to break, for example, RSA encryption or so, needs to factor this integer into prime numbers, and it's very hard. But a quantum computer can use a different algorithm that is exponentially faster in calculating these factors of the integer. So that means that a quantum computer can more easily break this integer into its two factors, and then it has a private key, and then it can decrypt your communication and so. So this is the core reason on why post-quantum cryptography is dealing with with new algorithms that are not vulnerable to this thing. On a classic computer, if a classic computer needs to factor an integer, the amount of time that it needs grows exponentially with the number of bits. And here we have exponentially, and since COVID, people have a better understanding on what it means exponentially. So that's an unfortunate side effect of the corona crisis pandemic. So if we add just 1 bit, if we make our keys 1 bit longer, then the time to crack it might double, for example. So if computers get faster and faster, then we just give keys more bits, which is easier done than doubling the performance of computers. So even with all the computers on Earth combined, the typical encryption algorithms are safe. But a quantum computer needs less time to decrypt, to factor an integer. It's the light gray arrow there is the time that it requires a quantum computer to factor an integer based on how many bits that integer contain. And you see that if we make the key longer, if we add more bits, it will require a bit more time, but it is more polynomial time, which means it might be, it will grow the time, but it will not exponentially grow. So by adding 1 bit, the time will not double, and so. So that's very briefly about why a quantum algorithm, well, not really the why, but how a quantum algorithm can be a real danger for these classical algorithms. I will very briefly explain, but really extremely briefly, why a quantum computer can do this in 27 minutes from now. Yeah. But how do you do this in Java? I have a few samples that are using JBang. Are people familiar here with JBang? Who is familiar with JBang? Okay. I expected more. I wanted to be hip. So basically, just the first line tells you what dependencies are needed, then you can just execute this with JBang. But it's a Java application, so you can run it with any IDE. And so if you have the dependency, the dependency on strange, which is a Java library that contains quantum algorithms. And if you would run this application, you see the screenshot made output. Yeah, you really see that it's a screenshot because I have my Ctrl+C even there. And I have 2 spaces between JBang and high level. But this is the output of the program. You see that we wanted it to print a factor of 21 is, and then that factor, and it did that also with some debugging information in between. So this application showed that 21 can be divided by 3. And if you know it can be divided by 3, then you know 21 divided by 3 is 7. So then you know 3 times 7 is 21. So that's the this is in Java a quantum algorithm. So what happened? We used a quantum algorithm. It's actually called Shor's algorithm that finds the prime factors of an integer by leveraging quantum physics behavior. And I'll come back to that later. But we invoked that algorithm on a quantum computer, but not a real quantum computer. It's just on my laptop. Well, no, on my Linux desktop, because I can't program on a laptop really. But it's not really a quantum computer, it's a quantum simulator in Java. And if all goes well, I can show the Java doc for this, the classic class. So I think if I go back here, you see that we imported the Oracle of Exchange algorithm classic class, which is from the strange library which I wrote, and which has a few quantum algorithms: find the periodicity of a function, factor an integer into its prime numbers, take the sum of two integers, search using another quantum algorithm through an unstructured list and find the item that obeys a specific function. So those are the quantum algorithms that you can use with this with the strange library. I have to admit that there are not many currently known quantum algorithms, so there are still lots of research going on in finding what is a good quantum algorithm that has practical use. If you hear about quantum supremacy, where a quantum computer outperforms a classical computer, this is typically about totally useless applications. And that is important to show that the quantum computer can indeed be much faster. But it's not easy to find algorithms that are immediately of practical use. But extremely smart people are searching for that. And basically, that's mathematics. So I always tell people what is the most important thing. If you're at school, if you want to learn one thing, learn your mathematics, because that is really the basic of quantum algorithms and more. Then I can probably continue in PowerPoint. Whoa, that worked. So now fasten seatbelts. Unless you want to leave, don't forget to unfasten your seatbelt. So we'll dive a bit more into quantum computing. I made the font size a bit smaller. So what is special about quantum computing, and how is a quantum algorithm different from a classical algorithm? And the key answer, or at least part of the key answer, is that we're using different building blocks for a quantum computer. The building blocks for a quantum computer and a classical computer are very different. But the good thing is that at a high level, what you saw in one of those previous slides, you can use Java. And the implementation will make sure that the different building blocks are used. So that is, as a Java developer, the short answer is, do I need to know something in particular about quantum computing? The short answer is no. The long answer is, well, you need to get an understanding what kind of problems might be good to outsource to a quantum algorithm. So let's talk about those building blocks. In a classical computer, the building blocks are bits. Everything we know, everything that's going on in a quantum computer is created with bits. And a bit exists in a logical way, where we use it in a program, but it's also in a physical, it has physical representations to store it in memory, on a disk, on a USB stick, through the network. But the software developer typically doesn't know, have to worry at least, about what is the physical implementation of this bit. I mean, nobody really checks how the zero is that from your application is sent over the wire to another computer, to a hard disk, and so you just use the logical representation. But still, it's important to, I'll briefly dive into the physical representation, because that brings us to the quantum bits. So the logical bit is 0 or 1, and we use gates to manipulate those bits. So, for example, the NOT gate will flip a 0 in a 1 and a 1 in a 0. And an XOR gate will, if we have a 1, 0 and 1, 1, it will have an output 1. So gates is something that we use in quantum computing as well. Some gates are similar, other gates are different, but that is the same. But in classical software, everything comes back to those bits. And the only thing that a computer typically does is just transforming boring arrays of zeros and ones into other boring arrays of ones and zeros. And that is the source of almost everything that we are creating these days, be the enterprise development, games. And I was wondering myself why I had that watch there. I don't know. So how do I have a physical, what the physical representation of a bit? And now I come into area that I don't understand. I think in memory we use voltage-based bits, where if we send a low current through a transistor, if it's low enough, then the bit is considered to be 0, and if it's 5 volt, then the bit is considered to be 1. So that's how a bit is represented in the memory of a computer, by using a physical process, by using a physical property, voltage, current. But there are also different ways. For example, the magnetic orientation of a bit, using magnetic orientation is what was used on hard disks, for example, to store bits. With magnetic orientation north-south, you could make a distinction between 0 and 1. So we use physical processes to store and to work with bits, and that's great. And we do a lot with it. Too much sometimes. But bits are not the traditional bits are not the only natural phenomena, and that's why we now introduce the qubit. Let's now talk about the qubit. A qubit is the quantum equivalent of a bit, and it leverages phenomena from quantum physics, which by definition already means that we're going on a much smaller scale, much smaller than bit representations. And we are going really close to nature. We're going to use the building blocks of nature itself to create a quantum computer. And that is, I think, one of the interesting things. If you think about a computer, it's extremely artificial. We're creating transistors which are huge compared to the fundamental particles in nature, while we have particles that are ready to use and that also have these properties of 0 and 1. For example, the spin of an electron. Spin is a property of an electron, a very small particle. And that spin can be have different values. It can have the value up, spin up, which we can say, for example, that's 0. And it can have the value down. So if we observe a particle, we can measure it. We can see its speed, velocity, position, spin. It can be up, down. But the spin can also be in the spin of an electron can be in a superposition of up and down, which means, my personal explanation is, it can be up and down simultaneously. So. And this is not something that we invented just to make quantum computers working. This is really how nature works. So this is something that is often hard to grasp for our brains. How can this be? This is actually the quantum equivalent, well, the real equivalent of Schrödinger's cat that is dead and alive at the same time in a box. Most of you probably heard that story. Poor cat. And it's by the way, no electrons were harmed in this presentation. But having a property that's a combination of two properties is something very weird, something that we don't have in classical computing. But you can think about the complexities, but also about the opportunities. Now, there's one big thing that we have to mention. The moment that we measure it, the spin will be either up or down, and not in a combination anymore. So, and that's the same thing as Schrödinger's cat. The cat is both dead and alive in the box until you open the box and you see it. Then it's dead or alive, but not dead and alive anymore. If that sounds strange to you, yes, of course it is. Do I understand it? No, by no means, totally not. There are many bright physicists working on explanations, and we can talk for hours about this, but there are, the cool thing is you don't have to understand it to create nice applications out of it. It's just something that it's proven with many experiments that the superposition phenomenon exists in nature, and the moment that you measure something, whatever the definition of measure is, that's a whole different story, you will only measure one of the possible states, another combination anymore. So if we compare the bits from a quantum computer with a classical computer, there are some similarities. On a classical computer, we would say if we have a value of 0, we call it a Boolean, which is false. And in a quantum computer, we have a qubit, which we denote with typically with Greek letter between, and in this bracket notation where we have first a vertical bar, then psi, and then the greater than thing. So that's how we denote qubits in quantum computing. And it holds the value 0. And on a classical computer, when we have a bit that's 1, we say it's true. We say it's a Boolean true. And on a quantum computer, we say it holds the value 1. So you can compare that with the spin here. Spin up is 0, spin down is 1, or the other way around. But then the quantum computer has this new state, which a classical computer does not have. Our qubit can be in a superposition of 0 and 1, which actually means that it is a linear combination. Whoops, there's my first mathematical term. A linear combination of 0 and 1. So it is a bit 0 and a bit 1. And the alpha and beta coefficients, that's my first Greek. Oh, no, the psi was the first Greek symbol. The alpha and the beta coefficients show how likely it is to be 0 and how likely it is to be 1 when you measure it. So this state of being both 0 and 1 simultaneously is something unique to quantum computers. So that's the physical property. Now, how does this translate if we go to the computing context again? As was shown on the previous slide, our qubit can be written as alpha times the 0 state plus beta times the 1 state. And alpha and beta are mainly probabilities. It means that, suppose that, well, one equation that I have to say is that alpha squared plus beta squared equals 1. So the probabilities sum up to 1. And I will not give more equations today. I don't promise because I'm not sure. But so if alpha equals 1 and beta equals 0, then the qubit reads as, then we know for sure that psi equals 0. Vice versa, if alpha equals 0 and beta equals 1, then we will definitely, if we measure it, we will measure 1. But if alpha is 0.3 and beta is square root of 1 minus 0.3 square, so a higher value, then there's a higher value that when we measure it, we will measure beta. That we will measure 1. So, and that is really important. So the last line here, when we measure this qubit, we will not measure alpha or beta. We will measure 0 or 1. That's the only thing that we will measure from a qubit. Whatever alpha was, whatever beta was, when we do a measurement, we measure 0 or 1. And we can simulate. We can simulate. I'm only going to say this in the next section. But we can show this behavior in a Java application. So with the strange library that I showed before, we showed the high-level APIs in the classic class. But you can also use the low-level APIs where you really can play with these qubits and gates. So what you see here is that we create a quantum program with 1 qubit, and we assign 1 gate to it. So we have 1 step with 1 gate. The gate is a Hadamard gate, which is something that a gate that we don't have in classical computing, but it is a gate that transforms a qubit into a superposition. And it's all gates, just like qubits in quantum computing have a physical representation, gates also have a physical representation. So I'm not making this up. With some cool laser show, you can change the status of qubits in practice. So, and that is actually how quantum computers work. Well, depending on what physical representation that they are using, but you can really change the state of this qubit. And that's what we do in this program as well. We tell it, start with 1 qubit, and here below you see a representation of it. So Strange uses JavaVex to visualize the circuits. which is another reason why Java is such a cool technology. With JavaFX, you have Java on the client and you can visualize all the scientific work that you're doing. The circuit that we created here starts with a qubit which is initially 0. Then we apply the Hadamard gate, and then we see that the outcome, if we would measure it now, we have 50% chance to measure 0 and 50% chance to measure 1. So 50% is the probability of the qubit. If we measure it, we will measure 0 or 1. I forgot to write the output of the program here, but you can run it yourself. If you're using JBang, you can run this immediately. What we are doing here is we have 10, so first we create the quantum program, which is part of the strange library. We render it here just to make sure that you can put it on a slide and so. Then we create a quantum execution environment, which is also part of a strange. And you have different quantum execution environments. Well, in practice, just one, but you could have different ones. And then we will run 10 times this program, where we run it each time from scratch. And if you would run this 10 times, you would see that on average, 5 times you will measure 0, and 5 times you would measure 1. So this is the difference between doing measurement and probabilities. So that sounds extremely boring and not performant. So then why is everyone excited about this? Well, the real value is not in the outcome, but in the probabilities. And we can play with probabilities during the whole processing. So remember, we said that we will only measure one value, but as long as we don't measure, those superposition states can survive. That's, by the way, one of the hard things to make a quantum computer. You want this, the moment that you do something wrong, or that the quantum state is influenced by the environment, then you lose the superposition. So it's hard to make them pure, and that's why, for example, superconducting qubits need to be cooled at a very low temperature until they find the superconducting material that works at room temperature, but that's not yet today. But the probabilities survive during quantum application. And that actually means that one qubit can hold two values, 0 and 1, with some probabilities that if we measure it is 0, some probabilities that if we measure it is 1. And two qubits can hold 4 values simultaneously, with some probability that if we measure it, we would measure 0, 0, some probability that we would measure 0, 1, another probability, and you know what I mean. So with n qubits, we have 2 to the power n values, and that is where the word exponential comes from. So with only 8 qubits, we can simulate 256 values. And on a classical computer with 8 bits, we have exactly one value. It's one value at the same time. That is, of course, you can then say, now I'm going to assign a different value to it. But the key thing here is that the quantum computer holds all these values simultaneously. You can do operations on those values simultaneously. So they will. I have a nice slide about it later. But so to be honest, but I already was honest. I rearranged the slides, so that's why I now says here that again that if we measure the system, we will only see one value. So no matter how large our application is, how much probabilities we had, what we measure will only be, so one qubit will only result in a 0 or a 1. And the alpha and beta values, they only exist during the processing. And I do remember when I gave a talk about quantum computing, someone asked me then, so I said this, and then the person asked me, so then what's the point in doing this? If you have this nice high performance processing, but you will only measure one value. And I thought maybe a good way to explain this is, maybe it's a bad way, I don't know. But in Java, we have streams, and some operations on streams can be done with parallel processing. For example, if you have this short program. Okay, so the first one who knows what the result of this get will be gets a T-shirt. What about that? Yeah, who was that? Oh, Gail. Whoa, we have a real mathematical talent in the audience. Can you? So indeed, so this is 9 because we have a list. We map every element to its square. We sort it by reverse order, so 11 square becomes first. Then we filter everything out that's lower than 10, and the first one then is, we filter everything out that's not lower than 10, and the first element then is 9. So what is done here in Java is this mapping process can be done in parallel. And that is going to speed up, well, if we have a huge list, then you know that some computations on strings can be done in parallel to speed up things. And then you're using more cores or more threads. And by using more threads, we can speed up our program. But of course, we're limited, because a thread in classical computing is managed by typically a thread pool, and is bounded by your hardware. If you have a CPU with 16 cores or so, even if you have a Loom with a virtual thread tons, of course, you will only have one carrier thread. Well, you have a limited amount of native threads that the processors support. Can be a large amount, but still, every additional thread will require more resources from your system. And that is not the case on a quantum computer, because the threads in quantum computing are provided by nature. I came up with that yesterday. That means that they are sort of for free. And the in my opinion, amazing thing is that this is really something at the fundamental parts of our of nature. So this is not something that we have to construct. It's really at the most elementary particles that show this behavior. The difficult thing is isolating this behavior so that you can leverage it. So because the moment that there was a nice cartoon about a qubit can be 0 and 1, but the moment that you watch, it becomes 0 or 1. So the moment that you try to move your eyes, it falls down to a state 0 or 1. So the hard part in quantum computing is not to interfere with the system. And as long as we don't do that, then we can leverage this parallel computing. The reason why I'm not sure that this is really a good example is because it might be well, it's not exactly the same. But I hope that with this you understand that a quantum computer that does computations on different values simultaneously is slightly comparable to what we do in Java with parallel executions on streams, for example. But the great thing is that a quantum computer does this for free. Now, always be careful when people say it's for free, because typically then they follow advertisements or so. Okay, one last slide for this fasten your seatbelt section, and then we'll go to something very digestible. Probabilities and measurement. So with this is a screenshot from Grover's search algorithm, which is a quantum algorithm that allows to find an element in an unstructured list. Oh, by the way, so I wrote this book, Quantum Computing in Action, because I wanted to understand how quantum computing was working, and I came up with lots of samples, and all those samples are in the book, but also online. And this one is something that you can find online. I will show the link later. What you see here is a quantum application with 6 qubits. You see them on the left there. And the result of this, I'm not sure that it's very readable. At the right-hand side, you see if we would measure this, what would we measure? And you see it's 99.8% likely that if we would measure that first qubit, that we would measure a 1. So, and the second one also most likely a 1, also most likely a 1, and then the 3 bottom ones are most only 0.2% chance that if we would measure them, we would measure once a day, or most likely 0. So if we execute this quantum application, we will most likely measure 7. But Strange has a debugger, so after each step you can show the probabilities, because during the process of a quantum application we only talk about probabilities, and what quantum steps are doing is changing the probabilities. And there's a bit more to it. They're also changing the phase, but I'm not going into that today. What you see there, the second arrow points to a very small green line that becomes bigger and bigger after each step. That is the probability of measuring 7 after step 1. And you see there's a fair probability, but the others, it's too small to show, but there's a much larger than 1% probability to measure the other values. So in total we have because we have 6 qubits, we have 2 to the power 6, which is 64 possible outcomes, and outcome number 7 is the most likely, and the more steps we do for this particular algorithm, the more likely that we will measure that one. So that shows how quantum computing is about, well, changing the probabilities and making the right steps to change the probability of the outcome that you want to be, well, to get to probability 1. So, and that is I actually plan to skip this slide because I see people on the second row with their mouth open. I can't see it in the last row, sorry, but it is. I just want to show it because I really want to emphasize that if you want to write quantum algorithms, which I highly recommend everyone to do, but it's not needed because you can use the high-level APIs as well, you need to think about probabilities and not really about the outcome. Well, also about outcome, but probabilities, that is where it is about. So I was saying that we are not running on a real quantum computer, but on a simulator. And how comes we can use a quantum simulator? Well, the physics behind quantum computing is pretty well understood. And there are devices, you can access them online even, some of them. They get better, they get more powerful. It's sometimes a hassle to sign up, and so, but you don't have to wait for those devices to be available because there are enough quantum simulators. So Strange is what I wrote in Java, but you have for other languages, other simulators, and they have the exact same behavior as a real quantum computer. Simply because we know how a quantum computer works, so we can simulate that behavior inside the simulator. And therefore, you can already write quantum algorithms or run them, create them, modify them, play with them today in simulators. And the algorithms that you write now for a simulator will also work later on a real quantum computer. And I compared it a bit with how Java FX is working internally. If a developer creates a rectangle, for example, and wants to show it on the screen, then internally JavaFX will call some, it's not exactly correct, but it will call rectangle.render content. And JavaFX has different pipelines to render content. For example, the software pipeline will do lots of calculations on the CPU, and then fill a frame buffer, for example, and show the rectangle. But the hardware pipeline will do most of the calculations, if possible, on the GPU, using OpenGL shaders or whatever, and they're leveraging the specific capabilities of the GPU, and then render the rectangle as well. But the interesting point is that for the developer, it doesn't matter. The developer just programs against the APIs that are then translated into low-level representations. So I see this similar to how quantum computing might work. We had this example in the beginning about factoring an integer. You can do that using the CPU. It will be extremely slow, but it's going to work. And you can also do that on a quantum computer, and it's going to be extremely fast, and it will work as well. So, and I think for some applications, the quantum computer is quantum computers are great. For other applications, they are not good. So this hybrid way of developing is probably getting more popular, I think. So almost there. The simulator that what do I have here? Oh yeah, I'm gonna skip this slide because I wanted to want to have one more slide explaining why how a quantum simulator works. I said we know how quantum computing works in reality. We understand the principles, so we can simulate them. Now, how does it work? Well, actually, if we have the status of a qubit and we apply a gate, applying the gate just means that we apply a matrix to the vector containing the states. So it's all about matrix multiplications that can be highly optimized, but in the end, it is multiplying a vector with a matrix and you get a new vector. So quantum gates can be simulated with a matrix, and then applying gates is just linear algebra. So that is how it can be implemented, and there are lots of optimizations possible in linear algebra. So that's the fun part, and that's what I really like to work on most. If you want to learn more about this, I have a step-by-step guide, because all the examples that are in the book are in GitHub as well, completely open. So let me... Oh yeah, by the way, so this is the... If you run the high-level Java API, for example, the search probabilities, what you will see is we are creating a quantum program here. And so the implementation of the high-level API is creating a low-level quantum application, adding steps, adding gates, creating an oracle, and so nothing to do with the other oracle, and then measure the value and give it back. So that is how the high-level API is working. And the samples that are going over the low-level API are in my Quantum Java GitHub repository, where you have, of course, a promotion for the book, and but the samples itself come with some explanation. So, for example, running the Pauli X gate, shows here what is happening, and so you can follow it more or less there, and it shows the UI that is expected to be shown. So you can browse through these samples. It starts simple and it ends more complex with Shor's algorithm, the one that factors an integer, and this allows you to play with it and to learn how it is working. So that brings me to the conclusions. So there are still many uncertainties about quantum computing. I have to be honest with that, but I don't see that as it's never going to happen, and we are safe, and so this is not a. I like to talk about opportunities, and I really hope that those opportunities will happen one day, and that that's actually why I'm honestly trying to give talks and so about quantum computing, because I want people to use this so that that person can find a cure for Alzheimer or cancer or so. So that is, or do a better model of our climate, and so it's really it is even if it's not 100% guaranteed that we will be able to do this, it's definitely worth. And I think as humans and developers, it's our duty to try it. You don't need a quantum computer. You can use a quantum library. If you want to use high-level Java, you can do that. If you want to dive into quantum algorithms, you can do that as well. And then I have some links here. And then I have 2 minutes for questions. Yes, there in the back. So the question is, since oh, by the way, you can get a book when the talk is done. Since simulators are based on linear algebra, have you considered using GPUs? Yes, I did. I haven't done it yet. Other implementations do it, but that is indeed one of the things that will speed up simulators. It will always be slower than a real quantum computer, of course, but that's why in Strange you have the quantum execution environment is an abstract class. I implement it in the simple quantum computer execution environment. I also have a cloud quantum computer execution environment, but it could also be a GPU quantum computer execution environment. Great question. Yes, there in the middle. No, 0 and 1.
Yeah, but probability of the 0 and the probability of a 1. You can sum them up to 1, I thought.
Yes, no, yeah.
For the author, so how is that two numbers?
So the two numbers are really just the 0 and the 1. So that is one of the real hard things to grasp, but it can hold 0 and 1. So it's not the alpha values, because then it would have infinite numbers. It would have 0.1, 0.2, 0.3, and so with the restriction that the squares sums up to. No, the thing is really that it can, so that if I have 3 qubits, I can hold the numbers 0, 1, 2, 3, 4, 5, 6, 7 simultaneously in memory, and I can do operations on those in memory. And when I measure it, then the alpha and the beta will determine how likely it is. I had a question, so over there, yeah.
Same question.
Okay, okay, great, yeah. Question over there in the back.
So, with n amount of qubits, like you can have 2 to the power of n values simultaneously, and those are all probabilities, I assume. Is that true?
No, yeah, it's actually the same question. It's and it's the most difficult thing to explain, and the probabilities are not the values. The probability is how likely it is that you will measure the value, and the value is 0 or 1 with 1 qubit. With 2 qubits, the 0 is 1, 2, or 3. No, 0, 1, 2. Anyway, 0, 1, 2, 3.
But then are these values all independent, or are there also some dependencies?
Okay. The question is, are these values independent or not? Well, I only talked about superposition, in which they are independent, but there's another great thing in quantum computing. Actually, it can be proven that without that, quantum computers would not be faster. And that's entanglement. So there can be correlated. I didn't talk about that, but that is really what gives the power, what gives even more power. Yes, in the front here. And that's the last. Then, if you have more questions, I'm walking around here, so time's up. So.
Are there resources for the algorithm? So is it easy to find new algorithms?
It's hard to find. The question is, are there resources for the algorithms? Is it easy to find new algorithms? No, that's actually very hard, and that is one of the most difficult things. So those are mainly scientific papers, but it's easy to find them, and there are many papers about the different algorithms. So about the existing algorithms, for example, Shor's algorithm is optimized many times, and there are many papers about it. But it's not that simple. That I mean. The ambition, if your ambition is that you want to create a new algorithm soon, that's hard. But there are scientific papers about how to do it. So thank you for attending, and yeah, grab me if you have more questions.